Section 13.14. True random numbers. All of the techniques for generating random numbers that have been discussed so far in this chapter produce pseudo-random numbers. Every book I have ever seen that discusses random numbers repeats the belief that it is impossible to produce true random numbers using software. This is because they are limiting themselves to a too narrow range of possible methods. In this section, I will present a workable method for producing true random numbers in bulk using software. All the methods in the literature for producing true random numbers depend on physical phenomena like cosmic rays, thermal noise, vibration, nuclear decay, and so forth. These methods are much too slow for cryptographic purposes. Instead, you can produce true random numbers by a three-step process. 1. Build up a large body of true random numbers taken from nature. 2. Make their probability distribution uniform. 3. Generate the random numbers by selecting and combining numbers from this corpus. The next few sections will detail how these steps can be done. Nature is full of randomness. The shape, coloration and position of every leaf on every plant and tree on Earth is random. They are the result of winds and breezes, sunlight filtering through the foliage, nutrients flowing up from the roots, raindrops and hailstones that have struck the foliage, insects that have chewed it, birds, squirrels, ground tremors and many other factors. Every wave on every ocean, every plant and rock in every desert, every ripple on every river, every cloud, every shell on every beach is random in size, shape, colors, location, orientation, and sometimes velocity. Some of this randomness can be captured simply by photographing these locales. You don't even need to leave home. Just take a handful of popcorn and drop it on a patterned surface. You can also use your own photos of people you know and places you have been. There are photos you have downloaded from websites and emails. There are hundreds more that have been placed on your computer by the operating system and by apps you have. There are billions more photos you can find using a web browser. As an experiment, I invented a pseudo word ZRMWKNV and searched for images. I got over 6,000 search results with pictures related to ZRMWKNV, and some of those sites contained hundreds of images. Section 13.14.1. Lagged linear addition. Each such image file contains lots of randomness, particularly if the resolution is high, but the distribution of byte values is far from uniform and far from independent. The distribution can be flattened out by using lagged linear addition, treating the whole image file, including the headers, as one long byte string of length L. Here is an example. The subscripts wrap around, as always. 3 passes, as shown, are sufficient, but feel free to use more. You don't want the frequencies too uniform, because that would no longer be random. If you want to use a streamlined version, like xn equals brackets xn plus xn minus 179, mod 256, note that 5 passes are needed. Be sure to use a different lag on each pass. There is nothing special about these coefficients, 7, 31, et al. I picked them arbitrarily. They may be any odd integers from 1 to 255. For each pass, the lags 40, 1581, etc. should be chosen so that one lag is considerably larger than the other. Small step, big step. One idea is to make the smaller lag about the cubic root of L and the larger lag around about the cubic root of L squared. For example, if the image file is 1 million bytes, you might make the lags about 100 and about 10,000 respectively. The smaller lag could be chosen between 50 and 200, and the larger lag could be between 5,000 and 20,000. Following the lagged linear addition with a keyed simple substitution makes it harder for Emily to reconstruct the image file. Section 13.14.2 Layering images. Another way to construct a true random sequence is to take two images and layer them one over the other using some combining function such as XOR or add, see section 13.1. A good method would be to perform one pass of lagged linear addition on each image before combining, and a final pass after they have been combined. Three images can be combined bit by bit using the nonlinear majority function, section 13.10. Again, I suggest one pass of lagged linear addition on each image before combining, and a final pass after they have been combined. This method can be used even when none of the three images are the same size. Align one short image to begin at the same point as the largest image, and the other short image to end at the same point as the longest image, like this. Where only two of the images overlap, add them bytewise modulo 256. Where all three images overlap, combine them bitwise using the majority function, or use a linear combination modulo 256, such as Cn equals brackets 113xn plus 57yn plus 225zn mod 256. The coefficients may be any odd integers from 1 to 255. An alternative approach to aligning the images is to extend the short images by repeating them. In the example, the X image has 22 bytes and the Y image has 33 bytes. The X image can be extended to 33 bytes by repeating the first 11 bytes of X. This way, the majority function can be used in all 33 byte positions. In practice, these images would have millions of bytes.